Hey everybody, welcome to EadsyAstronomy again. Told you I'd be back today. You're probably going to hear some background noise from my wife watching TV. Our office is part of our master suite. So anyways, I apologize for that if you can hear that. I wanted to talk about two papers that I looked at today. First one is the title of this podcast, we'll just call it Cosmic Collisions and Type 2 Supernova and Mass Loss Right Before They Explode. I said three articles. I'm going to take this part out because this is what I'll post on Patreon, but we're just going to get there. I'm going to be talking about an article today from Hubble Space Telescope that captured catastrophic collisions in a newly planetary system for the first time. Hubble was looking at Folmahault in Pisces, and Folmahault is the 18th brightest star in our night sky. It's about 25 light years from Earth, and they noticed that as they were doing this, there was a point of light that wasn't there in previous observations using Hubble images. Astronomers believe this signifies that they were witnessing the impact of two massive objects with a huge debris cloud. And actually, let's go back in time, 2008, using the Hubble Space Telescope then and images, astronomers identified a candidate planet around Folmahault. What was significant about this was it was the first stellar system with a possible planet that's been identified visually with visible light. They named the object Folmahault B, and while searching again for Folmahault B, astronomers instead recognized and correctly identified the object's true nature, that it's a cloud of dust created by massive objects, planets for example, smashing together. This was fantastic, but their discoveries didn't end there. As mentioned, the Hubble Space Telescope in its latest observations have uncovered a second point of light. One astronomers feel is a second debris cloud separate from the first one. It's a similar collision between large objects again. What amazed astronomers is that these two events were detected within a couple decades of each other, and that's something that theory predicted would be far less frequent in the formation of planetary systems. What is so cool about this is that these collisions are not just background noises. Their proximity to the star's debris belt suggests what they're actually seeing is a burst of activity within this planetary system. It's comparable to what probably happened early on in our own chaotic era when our solar system was new and was forming. It's pretty cool. It's almost like looking back, and we'll be able to learn things that happened in our solar system. Some things will be different, but we'll be able to apply that. Also, a takeaway that astronomers are taking from this is these dust clouds can pretend to be planets in images that are taken. The original planet, Folmahault B, was revealed not to be a planet at all, but a debris cloud field. These astronomers have learned that not every point of light they're looking at visually through images is near a star. It's actually a planet. Instead, the light could be transit debris clouds that occur from collisions from large objects that are telling us that as we study direct imaging missions in the future, we got to understand what's occurring when these points of lights are discovered, what's actually going on within that system, that debris system. Moving forward, astronomers have secured more telescope time using both the James Webb and the Hubble Space Telescopes to monitor the evolution of these dusty clouds to identify how they change over time. Do they brighten? Do they expand? Do they dissipate and go away? Or are blasts other parts of planetary disks? With James Webb, astronomers are going to be able to measure the dust grain properties and determine if ice is present to give us clues about planetary system chemistry and evolution. It's awesome. So this is exciting for us because it's the first time actual collisions of planetesimals around a star, in this case Folmahault, have been observed. It's significant because we're seeing in real time how the building blocks of planets come together in real time. This is like looking back when our own sun and solar system were forming, and they'll provide us hints and knowledge as we continue to learn more about how this system around Folmahault is coming together. Next, in the article Dance to Demise, How Massive Stars May Form Dense Circumstellar Shells Before Explosion, by, and I'm going to massacre their names, Surutri Sengupa, Dasuit and Arkaprabha Sarangi. The authors investigate what happens to red supergiant stars in the final centuries to decades before they explode as core collapse type 2 supernova, and why so many of these type 2 supernovae appear to be surrounded by an unexpected dense circumstellar material. Here's the problems here's the problem astronomers face. Observations of many recent type 2 supernova, such as SN 2023 IXF, SN 2005 IP, and supernova 1998S, show that they had bright flash ionizations lines right after they exploded. They also had strong X-ray and radio emission, and all this provided evidence that there were dense gas very close to the star prior to its explosion. Standard stellar evolution models struggle to explain how so much dense gas could be present so close to a star just before it explodes into a supernova. The authors, what they did was to decide to model a single red supergiant stars, individually many red supergiant stars, but one at a time, with initial masses between 12 and 20 solar masses, using very detailed MESA stellar evolution simulations. Their study focused on late-stage nuclear burning, i.e. the carbon, neon, oxygen, silicon, magnesium stages of nuclear burning within a star. And I will post, when I post the article, I got some images that show you the stages that a star goes through in shell burning, and then how long each of those stages actually burn. So as they were studying, they started with neon. Carbon to oxygen goes about 600 years. Oxygen to silicon is about 6 months, and silicon to iron is about 1 day, and the core collapse takes about 1/4 of a second to actually come down. Anyway, little squirrel there. They also studied how pulsation-driven instabilities in the star's outer envelope and how these instabilities can trigger violent mass loss events. We know that the star Betelgeuse, for example's great dimming in late 2019 through April of 2020 was a result of the ejection of hot gas that cooled and formed a dust cloud, blocking light from the star. Could that have been a pulsation event within the star that formed that to come out? Interesting. Don't know. I'm not an expert on that. We'll leave it to the experts. In the models, the authors did not assume that there would be a smooth, stray winds, and instead focused in their models of having a pulsation-driven superwinds and shock-induced dynamic ejections that mass loss would be time-dependent in the final stages of the star's life. What did they find? That massive stars can shed excessive amounts of mass shortly before exploding. The models naturally produce brief but intense mass loss episodes. The rates were about 10 to the -4 to 10 to the -2 solar masses per year, and they occurred in the last decades to centuries before core collapse happened. Note that this is much higher than the classical red supergiant wind rates in the past. They also found that these eruptions formed dense circumstellar shells very close to the star. Densities were in the greater than or equal to 10 to the -15 gram centimeters cubed. That matches closely the density and location of CSM inferred from observations of interacting type 2 supernova. The study and its observations show that single red supergiant stars no longer require exotic explanations for these heavy density dust clouds near them prior to explosion that possibly result from that. In the past, we say they would result from possibly from binary interactions, stellar mergers, or unusual external triggers. The observations naturally explained flash ionization features, early X-ray and radio emissions, and strong circumstellar interaction signatures. The key driver here are the pulsations. As the stellar core rapidly evolves in the final burning stages, energy leaks into the envelope and large amplitude pulsations develop that form shocks that eject material episode by episode. Basically, the star dances itself apart before collapse. I find that interesting, and I'm going to squirrel again here, away from the paper for a second. I almost posted about this a while back, but I thought it was too far. I love the article from August 28th this year, 2025. The article that NASA, and I have it linked here, called NASA's Chandra Reveals Stars Inner Conflict Before Explosion, where the authors there share this. Our research shows that just before the star Cas-A collapsed, part of the inner layer and larger amounts of silicon travels outwards and broke into neighboring layer with lots of neon. This is a violent event where the barrier between these two layers disappeared. Okay, pulsations. This upheaval not only caused material rich in silicon to travel outwards, it also forced material rich in neon to travel inwards. The teams found clear traces of these outward silicon flows and inward neon flows in the remains of Cas-A supernova remnant. If you go to the link and look at the article, they actually have it highlighted in images there. Small regions rich in silicon but poor in neon are located near regions rich in neon and poor in silicon. The models in this current paper that I've been talking about seem to match the evidence found by Chandra and the models used in that paper. Found that kind of interesting. I may be extrapolating too much here. I like to do that, and I'm not an expert. But I find connection, and I also think it directly links to the NASA Hubble article on Betelgeuse's great dimming in 2019, late 2019 through April 2020. Got a link here for that. I think what we're seeing, what is modeled in this current paper, is perhaps showed in Betelgeuse's great dimming. Did Betelgeuse have a pulsation event that ejected material out near it that formed dust particles that blocked Betelgeuse's image dimmed it during that time, and then eventually moved away and dissipated and went away? Do stars go through several of these pulsation events? Could probably be part of this. Okay, getting back here. Anyway, like I say here in the paper, I'll let professionals piece all of this together. What they'll need is actual evidence to make the connections, and I understand that from the scientific method. I just think it's fun to extrapolate a little bit here. The work in the current paper helps us to resolve a long-standing mystery of why do so many Type II supernova explode into dense material that seemed to have been ejected only shortly beforehand. It also has a much broader implications for supernova light curves, modeling, radio and X-ray diagnostics, dust formation in supernova environments, and understanding how such massive stars die. Massive red supergiant stars may experience violent pulsation-driven mass loss shortly before death, creating dense dust shells of gas that dramatically shape how the supernova looks to us. It seems that, could Cas-A have had a major pulsation event, and the one that they link here was the final event, and did it all that dust and material really blind Cas-A, besides the interstellar medium dust, from us seeing its explosion? Interesting. It's a question I would ask a professional and see what they think about it. Massive rich supergiant stars may experience these violent pulsation-driven mass loss shortly before death, creating these dust shells like I talked about. It seems that some of these stars aren't going to go quietly into the night, into the stellar history night, but instead they appear to shed their outer layers in a final unstable phase, setting the stage for some of the most luminous and complex stellar fireworks that we will ever observe. Again, for me, I take away a couple questions. Did the star that formed Cassiopeia remnant undergo creating such a shell of gas or pulsation before it exploded, and then again in its final moments? Did that help to blur it from being seen here on Earth, besides just the dust in the interstellar medium where it was? Also, is this what we saw in 2019 to April 2020 on Betelgeuse, that a pulsation caused a massive mass loss and the dust particles blocked our view? And is that a sign that Betelgeuse is getting ever closer to becoming a core collapse supernova? And I know that Betelgeuse isn't going to happen anytime soon relatively to our time span. In a stellar time span, it will be soon, but not in our time span, hundreds of years probably, maybe even thousands. But are we witnessing the beginning of the end of Betelgeuse, and can we expect more dimming events as Betelgeuse perhaps has more pulsation events? Is the pulsation event happening decades, centuries before the death? So is Betelgeuse a model that we can apply from this paper to an actual star and trace and see if the model actually works? that's kind of exciting to me. Again, I love supernovas. I love everything to do about them. Would love to see one happen, a nearby one in our lifetime, but not too near. Uh, but I would love to see one at a safe distance go off, even if it was a Type 1A. And I think that would be very exciting. I love how these papers just bring questions, and I hope they bring questions to you. Hope your skies are clear. Mine aren't. I've been very clear about that. They won't be for about a week. And but life is good. Personal life is all clear and good. I hope yours is too. Have a great night. Talk to you soon.